Greetings and welcome to another installment of QuanSlot. This is 43 in our basic application series, Lucky 43, and this time around part 4 of our epic Simple Linear Regression series, a brief history of regression, an extremely brief history of regression. Okay, let's jump right in here. Immediately after the Great Pyramid Fire of 5000 BC, John P. Regression, angered by the recent failure of his pimento cheese hot pocket, invented regression. And ever since, high school students and college students alike, both, by the way, prolific consumers of non-pimento cheese hot pockets, have been anguished over the study of regression. Yeah, that wasn't so bad. Okay, well, I gotta come clean here. Of course, none of that happened. There was no Great Pyramid Fire of 5000 BC or John P. Regression. I was really hoping we could shortcut this. History's kind of tough to do. Okay, I got an idea here. Oh, by the way, what you just saw there, if you caught that, first ever QuanSlot jump cut. Let's take a look at our previous video's QuanSlot challenge. This is from part 3, the previous installment. The simple linear regression line is the least square solution. It is sometimes loosely referred to as the conditional mean or conditional average of our response y given a value of our predictor x. Strictly speaking, empirically this is not true, and previously we looked at a simple example involving 4 xy pairs. In this example, we have one point where x is 1, the corresponding y value is 1. However, the least squares line returns a value of 3/5 when x is 1, and 3/5 does not equal 1. Now, it turns out that there is a particular scenario where the least square solution will always give the conditional average, and the challenge question is, what is this situation? Well, the answer, when the domain of x contains exactly 2 values. Now, recall that an attribute's domain is a collection of its unique values. Whenever our predictor's domain contains 2 unique values, our least square solution will be the conditional average of y given x. And just to offer a simple example here, our domain of x is 0 and 1. The conditional average of the 4 y values where x is 0 is 0. The conditional average of the 4 y values where x is 1 is 2.5. Our least square solution is the line y equals 0 plus 2.5 times x. So when x is 0, this function returns a value of 0. When x is 1, it returns a value of 2.5. There you go. Moving on. Now, there are many sources that offer academic histories of regression. Here on QuanSlot, we like to consider a diversity of perspectives. Like most all inventions, discoveries, or advancements, linear regression can be viewed as a consequence of the confluence or coming together of past ideas and developments. We could say the regression arose as a consequence of 3 conditions: the desire to express relationships mathematically, properties of geometry, and the growing recognition that error seems to seep into human observation. Always with the error. Okay, now the appeal of expressing relationships mathematically is ancient. It goes way back. So for example, the area of a rectangle equals the product of its height and width. It could also be the relationship between assets in commerce, like 1 new pair of work shoes equals 4 gallons of pickled peppers. Or it could be converting units of measurement, like 4 gallons of pickled peppers is about 1.72 pecks of pickled peppers. Yes, a peck of pickled peppers, only here on QuanSlot, folks. Okay, geometry. Now, in what follows, there's quite a bit going on here, but in what follows, we're using Euclidean space. Now, on a 2-dimensional plane, suppose I'm here, upper left, and you are here, lower right. Now, there's lots of different paths we can use to traverse the space between us. Actually, there's an infinite number of paths in Euclidean space. Now, when we think of the shortest path, we think of a straight line segment connecting our 2 locations, our 2 points, and it's unique. This is true in 3 dimensions as well, and in fact, it is true in 4 or 5 or more dimensions. Though we normally, admittedly, don't imagine ourselves moving around in high-dimensional spaces like that. Now, this shortest distance is computed as a sum of squares, particularly the square root of the sum of the change across each dimension. One could say that in human experience, the shortest path between two locations minimizes a sum of squares. It happens to be a least squares solution. Now, in simple linear regression, the regression line is the least squares solution, a unique line function that minimizes the sum of the square residuals. Now, we can relate this to the shortest path idea, although I have to say, the connection at first blush may not seem obvious. So we're going to consider a very simple example with 3 observations, okay? Each observation represents a dimension. So in this example, we have 3 dimensions. We can now identify a single point in this 3 space that represents the actual observed y values. And there it is, the blue dot there. We now identify a single point that represents the 3 respective y hat values. That is our least squares aligned solution at the respective values of x. So you see that, that's the green triangle there. Now, we can try using different line solutions, okay? We just move the line around. But any other choice of line solutions will move the y hat point farther away from the y actual point, and the least squares solution defines a y hat point that is closest to the y actual point. And if we think of the y hats as predictions, we can say that the least squares line solution assures our predictions will have the shortest Euclidean distance to the actual values. Okay, now error. Error in the broadest possible sense, okay? So conversationally, like we're including any source of variation, difference, inconsistency, or irregularity. Inconsistency and irregularity in the conversational sense, not the mathematical sense. Okay, we all know that if the same thing is measured more than once, we may likely get different results. And this could be because of instrumentation, method, precision, or wishful thinking, and the latter case of wishful thinking might euphemistically be referred to as just simply bias, but all of them fall under measurement error. Okay, measurement error. But there are other types of error. Okay, there's intra-class error, and then there's also inter-class error. So just as a simple example, if I ask you for the weight of an apple and you go into your kitchen, find an apple and weigh it, your measurement will likely be different than one I obtained by weighing an apple from my kitchen. And this is true even if the apples come from the same tree. Now, thinking about mathematics, if it is true that y equals a plus b times x, then if we have 2 data points, 2 xy pairs, the 2 x values have to be unique here, we can uniquely solve for a and b, the 2 function parameters. This has been known to mathematicians for centuries, okay? Nothing new about this. Broadly, we call this solving n unknowns from n equations. In this simple case, n is 2. 2 equations, 2 unknowns. However, suppose we have a third xy pair, and to our chagrin, we find that if we solve a and b using the first 2 equations, we get a different result than solving a and b using, say, the second and third equations. The notation here is very loose, by the way. Okay, there's no problem. We can simply add a unique residual or error term to each equation. However, here in this example, we now have 5 unknowns and only still 3 equations. And again, this is not a problem. We can impose some constraints on these residuals. We can require that they all sum to 0, and we can require that the sum of their squares be at a minimum. A and B now are our least squares solution, our regression solution. And it is this method that was employed a little over 200 years ago that marks the discovery of least squares regression, or the method of least squares. Now, the application then involved tracking celestial objects like comets and asteroids. Now, in scientific discovery, to be sure, there is often synchronicity, and this appears to be the case here. Who it was that first discovered the method of least squares is mired in controversy. The first published paper illustrating this method is attributed to Adrien Marie Legendre in 1805. However, some believe the discovery is owed to Carl Friedrich Gauss, who claimed to have employed this method some 10 years prior. 10 years, a whole decade. Now, we should note that both these early applications involved more than one predictor. Simple linear regression, our focus in the series, uses only a single predictor. So actually, they invented something more general, a little bit more complicated. Development of the modern flavor of simple linear regression is squarely attributed to Francis Galton in the late 19th century, almost 100 years later than the first applications by astronomers and mathematicians. like Gauss and Legendre. Galton coined the term regression to the global mean. It is really important to note that this name, regression, refers to a property of the result of applying the method of least squares to measurements of natural phenomena, not really to any property of the method itself, which I think is really interesting. Galton found that adult sons of tall fathers were often not as tall as their father, and that adult sons of short fathers were often taller than their dad. The heights of the children regressed to the average, the global average. By the way, in his book, The Lady Tasting Tea, David Salzberg points out that this result for Galton was both surprising and yet, after some consideration, obvious. Actually, a very interesting observation. Why do we say obvious? Well, suppose there was no regression to the mean, that adult sons were on average as tall as their fathers. What would the world look like? That's it. That's going to do it this time around. Thank you so very much for tuning in. Whatever you do, don't forget to stay tuned for more QuanSlot.